the sun and its variability affects the Earth in two ways: through its irradiance, its photon output, which I've color-coded in yellow because the sun is yellow, and through its magnetic field and the variability of the solar wind and the interplanetary magnetic field, which is modulated by the magnetosphere. And I coded those in red because the magnetosphere is red. And then the things that are really terrestrial in origin, that come from the Earth itself, I've coded in blue because the Earth is a box of rain. And the combinations are things that are orange, for instance. The solar rotation modulates both geomagnetic activity and solar irradiance, and consequently affects the Earth's upper atmosphere through both of those mechanisms. That's true over the solar cycle and perhaps the variation of the solar cycle. Things that are in green are things that are affected by both solar irradiance and the Earth itself. And then here's an odd one. The evolution of the Earth's magnetic field is in purple because it happens on very long time scales due to things that are coming from inside of the Earth as modulated by magnetospheric events. So this is the talk I'd like to give. I don't have time to address all of these timescales and all of these effects. So I'm going to talk about this cluster in the middle, things that happen on timescale of a year or a decade or a season. And that includes the solar cycle effects, their variation, anthropogenic effects, to a certain extent the changes within a year. And I'll touch on geomagnetic effects. Don't forget the Earth rotation. The Earth rotation is very important. It brings us the magnetic field. It's responsible for Coriolis force and hence hurricanes and blizzards, other catastrophes. I'm aware that we're web streaming this to some of my friends on the East Coast, so I have to warn you that yet another periodic catastrophe is approaching the East Coast as we speak. I get this from my favorite and most reliable newspaper source. I don't know if you can read this. Millions of eyewitnesses watched in stunned horror. Traffic was bottlenecked for more than 2 hours in many major metropolitan areas. Scientists say they are unable to do anything to restore light at this time. Whenever you read scientists say, beware, the next statement is likely to be inaccurate. So here's what we're going to do in the meantime. I'm going to give a very basic introduction to the solar cycle. I'm going to very, very basic introduction to the thermosphere-ionosphere system, that part of the upper atmosphere that's most affected by solar variability. Talk about its variability, especially about a topic that we're very engaged in right now, which is the atmospheric drag on satellite orbits, the solar, and I'll mention the geomagnetic effects, and then the change of this system that's being driven by changes caused by human activity itself. Finally, we'll talk about the recent solar minimum, or fairly recent solar minimum that happened in 2008 and 2009 that occurred between solar cycles 23 and 24. The solar cycle is best known in sunspots. The sunspots are manifestations of magnetic activity on the sun and therefore indicative of the solar activity cycle. They've been tracked for a long time. The monthly mean is plotted in these dots, the annual mean in the red lines. And so two things are immediately striking about this, even if it's familiar to you. One is that there is a very periodic behavior of the solar cycle itself that is constrained roughly 10 to 12 years. We speak of the 11-year solar cycle. And yet, the magnitude of the solar cycle is quite variable. Now, I can't look at this plot and discern whether that variability from one cycle to the next is random or chaotic. And I use the word chaotic here to mean seemingly random, but with some sort of underlying pattern. We do know that sometimes the sun goes into protracted periods when things are fairly quiet, even during solar maximum. Just before this time series starts, there was a well-known period of time when there were little or no sunspots, even though we believe that solar activity continued on its same cadence. But it was very quiet back then. It was quiet during the so-called Dalton minimum, and then about 100 years later. And now we come to a time where it seems weak again. This cycle that is just peaking and just beginning to wind down, we think, has been a weak one, the weakest in 100 years. That solar magnetic activity cycle also manifests in other things that are driven in the active regions that are associated with the magnetic activity on the sun. This includes especially solar extreme ultraviolet radiation. These are things with wavelengths on the order of 10 to 100 nanometers. This is actually a plot of the 30.4 nanometer line of helium on the sun, measured by the SOHO satellite. And as we go from solar minimum in 1996 through the peak of solar cycle 23 and back down to solar minimum in 2006, you can see you can see the predominance of the active regions at solar maximum, and also you can see that the integrated flux is much larger at solar maximum. And that's even more true in the X-rays. Here's another one of these montage. This is from the Yoko satellite, and in X-rays this is on the order of 1 to 10 nanometers. And here we're going from the peak of solar cycle 22 down to the minimum and back up to the peak of solar cycle 23. And the variability at these wavelengths is even larger. It's like an order of magnitude. To quantify this, here's a basic model of the solar spectrum. Wavelength plotted on the x-axis in nanometers, log scale, and the radiance, the solar flux, in a very, very extended log scale on the y-axis. What I've done is I plotted the solar maximum spectrum in red, and then overplotted the solar minimum spectrum in yellow, so that the variability between minimum and maximum appears as this red fringe behind the yellow curve. Again, the sun in the visible being yellow, and you can see in the visible and the infrared the variability is negligible. It's on the order of 0.1%. On the order of 0.1%, essentially integrated over the entire spectrum. As you get into the middle ultraviolet, there is variability on the order of a few percent, but you can't even see it on this plot. This log plot, very, very large scale. As you get into the far ultraviolet, you can just see this 10% or so variability popping up from behind the minimum spectrum, and as we get into the extreme ultraviolet, the variability is in the order of a factor of 2. Sun roughly doubles from minimum to maximum in its output at those wavelengths. These are ionizing wavelengths in the order of 10 to 100 nanometers. Soft X-rays, and on into the hard X-rays, even more. Order of magnitude variability from solar minimum to solar maximum. This radiation gets dumped into the upper atmosphere, gets dumped through the atmosphere. Very brief introduction of the atmosphere. It's separated into spheres that are delineated by the local minima and maxima of the temperature profile. Troposphere is where we live. The stratosphere, where airplanes and balloons fly. We have the mesosphere. Often, as we get up here, we often are speaking of space. And the thermosphere is technically space, but it's part of the atmosphere. And because those solar extreme ultraviolet radiation and X-rays get deposited in the thermosphere, and because they are so variable, it drives an enormous change in temperature of the thermosphere. The thermosphere is hot because it has a hard time getting rid of energy. It doesn't have much in the way of molecules, especially heterogeneous molecules, to radiate energy. So it can only get rid of energy by conducting it downward to where it can be shed. And consequently, it's at high temperature and very variable depending on how much energy you dump into it. The atmosphere looks roughly like this. Another key delineation in our understanding of the atmosphere is this fuzzy boundary between a fully mixed atmosphere due to all the turbulent motions and a diffusively separating atmosphere. When I say diffusively separating, what I mean is that the lighter atoms float to the top. They follow their own scale height. They are not fully mixed into the gas. You can see that here, was in the lower atmosphere, in the middle atmosphere, the major species, molecular nitrogen, molecular oxygen, are fully mixed, and they have the same mixing ratio, and hence are parallel lines on this, again, log plot over in a very, very extended range. As we get up into the thermosphere, molecular oxygen drops off because it's being dissociated by all of that ultraviolet. We have atomic oxygen, which is lighter, and it follows its own slope and essentially floats above the molecular nitrogen, becoming the dominant species at higher altitude. So lower thermosphere, molecular nitrogen is dominant. Upper thermosphere, atomic oxygen is dominant. Here's what the solar energy deposition looks like as a function of wavelength and altitude. This is the absorption by ozone in the stratosphere in the middle ultraviolet and near ultraviolet. This is very fortunate for us because this radiation, all of this radiation, is fairly harmful to biological activity. This is the region of the spectrum that generates ozone by dissociating molecular oxygen. And all through the middle atmosphere, we have molecular oxygen being dissociated in the Schumann-Runge continuum and bands. As we get into the thermosphere-ionosphere system, this is the ionizing radiation. Extreme ultraviolet, soft X-rays, highly variable, highly ionizing. And so what that does is it creates an ionosphere. Here's a good look at what it appears to be, just focusing on that ionizing range, solar minimum, and then at solar maximum it intensifies, but it also rises up because the whole atmosphere is rising up. A hotter atmosphere is a denser atmosphere. So all of this ionizing radiation creates an ionosphere. Most of the ionization happens at fairly low altitude, but the ions go through a chemical diffusive process to form a predominant layer in the so-called F region around 300 kilometers, very variable, much higher at solar maximum, much higher during the daytime. So here's a solar maximum curve, day to night, solar minimum curve, day to night. The ionosphere continues to persist at night, even though the radiation has been turned off, simply because those O+ ions, predominant species in the ionosphere, are long-lived. So here's what the composition looks like. Oh, one more. The variability of the ionosphere and thermosphere sort of go together. A hotter solar maximum ionosphere means a denser, more extended thermosphere. Notice, you seldom see the ionosphere and the thermosphere plotted on the same axis because they're so different in density. But when you do, you will notice that even at the peak of the F region, the ionosphere is only ionized to the degree of about a part in 1,000. And in the E region, in the lower ionosphere, it's a part in 1,000,000. It's a very, very weakly ionized plasma. The ionosphere is mostly neutral, even though we often refer to it as the ionosphere. Its better known name simply because it was discovered first, bouncing radio waves off of it. So this is the basic variability of the thermosphere-ionosphere system as a function of altitude. Hotter at solar maximum, more dense at solar maximum, and the ionosphere following along. This is the composition structure. I won't spend a lot of time going through here. Just to emphasize it again. N2, molecular nitrogen, starts as a dominant species as it is throughout the lower atmosphere, drops off quickly. Atomic oxygen takes over as the most important species in the thermosphere, and consequently, atomic oxygen ion, O+, is the most important species in the upper ionosphere. So, how are we doing on time? Spent the first half of this talk trying to convince you that the thermosphere is highly variable, that it's hotter. When it gets hotter, it gets higher, and that it's hot because it has trouble shedding energy, and it's mostly atomic oxygen. And all those things are true, but not for long, because the main elemental composition of the thermosphere and exosphere above the thermosphere will ultimately probably be aluminum and titanium and molybdenum. I just like saying molybdenum. You know why. Now, that's a slight exaggeration, although it is true that the magnetosphere is made up almost entirely of aluminum at this time. But in low Earth orbit, the predominance of orbiting objects of man-made construction, most of them inert, most of them just pieces of space junk, has become spectacular. There are over 10,000 objects in low Earth orbit being tracked by the Department of Defense and by the NASA Orbital Debris Program Office, which makes these really nice graphics. Found these on the web. You can find them too. I also found this one on the web, which is really spectacular. It's an animation taken from the actual two-line elements of the tracking data of all the objects in low Earth orbit, and you can throughout Earth orbit. And this is, in fact, this is geostationary out here, very crowded. All those communication satellites. As you come into the equatorial view, you can see there's also a population of geosynchronous, but not geostationary satellites. Like, oh look, there's SDO. And as you come in to the objects in middle Earth orbit, you can see, again near the equatorial, oh look, there goes one of the Van Allen probes. But look at the incredible cloud of things flying along in low Earth orbit, below about 1,000 kilometers altitude, that, yeah, including cubes. Most of them are just pieces of stuff. I just remember when we launched the Snowy satellite, just a little satellite, but bigger than a CubeSat, but four things went into orbit. The shroud, our satellite, the adapter ring, and the experimental blasted orbital was putting up. Now they're all gone because they were in fairly low orbit, and their orbits decayed. But there's so much stuff up there, and this is the altitude that the space station flies at. Here's a polar orbiting population, sun synchronous, and then the animation zooms back so you can see again that geostationary ring. It's fascinating stuff, but not just to space junkies anymore. There's a significant popular appreciation for the importance of space junk. Orbital debris. I haven't seen this movie. I've been told that it's actually quite good, that it's scientifically reasonable. It does a reasonable job of. Correct me if you've seen it and you have a different opinion, but basically the premise is the two astronauts, very attractive astronauts, are on their space station when an explosion elsewhere in space sends a cloud of debris hurtling toward them, and that has deleterious interactions with their vehicle, i.e. the International Space Station, and it all happens in eerie silence because, of course, in space, nobody can hear you scream. So this is just a recent movie, but as the New York Times has pointed out, this is not just a Hollywood fantasy. The villain is space junk. And the article goes on to say that this is an important issue facing society on an international level, and of course they recommend mitigation. The primary means of mitigating space junk is to stop making space junk, to have deorbiting plans, and not blowing things up in space is very important. But we have to do something about the stuff that is there, and that largely consists of attempting to track it. Tracking is very sophisticated. That naturally leads to prediction. Due to Kepler's laws of motion, prediction is easy in a perfect vacuum. But the atmospheric drag exerted on all these objects, and particularly the ones in low Earth orbit, is still a significant uncertainty. The greatest uncertainty. And ironically, despite all the work we've put into it, the operational models that are used to track satellites are still the basic empirical models that were developed during the 1970s, not even the fancy empirical models such as MSIS that you might use in your research, but really old stuff like IKEA 77. Now they've been making some improvements on these empirical models, but they're still using very, very coarse and geomagnetic and solar activity indices as inputs, which we know have limitations. And we think that it's really time to try to move this field forward in the way that meteorology is moving forward, by using physics-based models to predict atmospheric motions using the principles of physics. And I use the words physics-based advisedly. Saying physics-based implies that there's some other basis for scientific research, and probably isn't. Even empirical models are physics-based. Now, ironically, I don't know if it's ironic, but to close this circle, it turns out that one of the best ways we have to improve our models, to validate our models, to understand if our models are doing anything realistic at all, is the tracking data from those very objects that we would like to be able to help the DoD track. Because by looking at the change in orbital elements, you can infer what the atmospheric density is doing. Now, the model that we have been using mostly to try to compare to satellite drag observations is the NCAR TIE GCM, original developed by Ray Roble, Art Dickinson, Art Richmond, and the whole team here. It's the atmosphere-ionosphere piece of the CMIT model, which is what we call this when we couple it to a magnetospheric model like the LFM. It's available at the Goddard Community Coordinating Modeling Center, or simply by going to the website here and downloading the code and running it yourself, or just going upstairs. And it can now be run from solar, wind, and IMF inputs using the Weimer formulation. This paper just describing how we do that. This is just a nice animation of what the model looks like in response to a major storm. This is it's actually the famous AGU storm of 2006. This is the lower ionosphere, the E region. This is where the aurora deposits most of its energy. And neutral temperature. The O to N2 ratio, remember I said these are the two major species in the upper atmosphere, and their ratio is indicative of vertical motions in the atmosphere. And then this is what comes out of all that is changes in the upper ionosphere, the so-called F region. So if I set that into motion, you will see the rotation of the Earth. Don't forget that. That's the day to night change. It's a big storm happening, and then waning. That in turn causes an evolution of the neutral temperature. Set that into motion. Here's the storm hitting. Notice it propagates throughout the thermosphere, not just at the polar regions. These great waves come spreading out. You can really see those waves in the way that this O to N2 ratio evolves. A big band of atomic oxygen spreading out from the pole and gathering at the equator. And because of the chemistry, that has a big effect on the F region. Both the electric fields and the neutral atmosphere causes the F region to change from it's already in a very structured state, but that structure gets disrupted in various interesting ways. I'll see if I can play these all together. There, now I got them playing all together. It's a little confusing if you try to watch all four at once, but I'll let it loop for just a minute so you can see how the storm kicks off the temperatures, affects the O to N2, and disrupts the ionosphere. So this is our modeler's view of the world. It's a very comprehensive view. It's not easy to quantify how well it's working. We do have, as I mentioned, a very good way of seeing how it's working in the aggregate through the measurements essentially made by this analysis of satellite drag on low Earth orbiting objects. So this is a comparison of the model in red and an estimate of the global mean density at 400 kilometers. It's a very important altitude because that's roughly where the space station flies. And this is a measurement made by John Emmert using an NRL by analyzing the orbital elements of virtually every object in low Earth orbit. And so this goes from the previous solar minimum up to the recent solar minimum and then to where we are sort of at maybe solar maximum. And there's several, well, first of all, I think that the agreement is really quite good for what we're trying to do here. You can see the immense solar cycle variation, order of magnitude in density from solar min to solar max. This very high density at solar maximum is not a bad thing. It tends to clean out the lower thermosphere. All of those orbiting objects, virtually everything below 400 kilometers, gets deorbited and burns up, we hope, or drops to the ground by the excessive drag at solar maximum. So these high densities are really a good thing. They're enhanced by some of these storms. Here's some of the famous ones, the 2003 Halloween storms. Here's that AGU 2006 storm. And the model is you can see that red dot and that black dot on a global mean daily average. It's doing a reasonable job. And we're also doing a very nice job of capturing all this seasonal variation, this annual fluctuation. There's an annual term and there's a semi-annual term in there. And as we descend down into solar minimum, we're in pretty good agreement with satellite drag data, and as we come back up. So, yeah. 2005. Right here? Here. Oh. You mean not just in the running average. What I got here is an 81-day average in the line, and then all the dots are the daily means. Right here, you spotted a very interesting thing going on here, which is that the response to these storms, although initially positive, you can also have negative responses to the storms, especially in the ionosphere. These storms generate a lot of nitric oxide. The nitric oxide leads to cooling. And you also can destroy a lot of ionosphere after you create a lot of ionosphere in these storms. So you have positive and negative effects. I think what happened, I don't have the resolution, and my, well, this is, I have to align myself. This is mid-2004, and I don't have we have to blow it up and look at this specific storm, but I think what you're seeing is a period of fairly low activity, followed by a big storm, followed by a recovery, and then back to normal. But there sure is a huge amount of structure in here, and if you look really closely, you might notice that we didn't do a really great job on that drop out there. A lot of this stuff, as I mentioned, is quasi-seasonal. Rodney. They're not. Most of those are not storm associated. I'm noticing that this one comes in accompaniment with this big peak here. All this stuff here that happens every year. This is that semi-annual annual term, which.
More on the 27-day period. It just looks like there are a lot of lone black dots on the lower
Yeah.
side of that, the red and black dots.
Yeah, and you notice that particularly at these plots, at these times when the atmosphere, every July, the thermosphere gets very low in density. Very difficult topic to understand, and not one we're going to talk about today. If you want to look at 27-day rotation, I'll have to show you another plot. I have it in backup. But at any rate, the purpose of this one is to show, first of all, we did an 18-year run, and it only took a week, and the model is working pretty well. And again, this high solar activity can be a very good thing because it cleans out from the point of view of the space junk that I wanted to use to frame the purpose of this talk. And when we are at solar minimum, when solar activity is very low and the thermospheric densities are very low, space junk tends to accumulate. And that's not a good thing, and it's getting worse. And the reason it's getting worse is because the thermosphere is cooling. The reason the thermosphere is cooling is the same reason that the troposphere is warming. Introduction of greenhouse gases, particularly carbon dioxide, into the atmosphere causes radiational changes throughout the atmosphere. In the troposphere and lower atmosphere, the net result is heating because carbon dioxide is radiationally active in the infrared. It traps outgoing radiation. In the thermosphere, the net effect is cooling because those radiational active bands of carbon dioxide emit, and you get radiational cooling to space. I said before that the thermosphere has a lot of trouble shedding heat. Well, one way it can do it is if it has just a little bit of carbon dioxide in it, it can translate that heat into the carbon dioxide and emit it out. And that happens throughout the middle atmosphere, but it's most dramatic in the thermosphere. This was predicted by Ray Roble and Bob Dickinson in 1989. very famous plot, which is why I show it from the original paper. Just look at the solid curve. This is a doubled CO2 case. You double the CO2, you get on the order of 50-degree decrease in upper thermospheric temperatures. And we are on a path to doubling CO2, although we're not there yet. Cooler temperatures means lower densities. So the densities are dropping, and that exacerbates the whole space junk problem. So since that prediction, there's been a lot of effort to try to observe whether it's going on. This plot by Jan Lestevica, who's one of the leaders of that project, tries to capture what we think is going to happen and what we are trying to measure. The ionosphere is very confusing. If you saw the seminar by Ingrid Knosson a couple of weeks ago, the ionosphere evolves not just from the sun and anthropogenic acids, but also from the changes in the magnetic field. It's a very confusing picture in the ionosphere. It's very dynamic anyway. Middle atmosphere should be cooling, but it's not easy to measure. The two things we know for sure on this plot is that the troposphere is warming and the thermosphere is cooling. And the reason we know the thermosphere is cooling is because of the satellite drag data. Now, I showed you all that solar cycle variability. How could I possibly know, in the face of order of magnitude solar cycle variability, that the thermosphere is steadily decreasing in density? Well, one way you can tell is you go from one solar minimum to the next. And that's what Jerry Keating did in the landmark discovery in his paper in 2000 that the cooling predicted by Roble and Dickinson is in fact occurring at a higher rate than expected, about 5% per year. And, sorry, one of the pitfalls of this field is we keep speaking in decades versus years. 5% per decade is the observed decrease at solar minimum. Now, since Keating's findings, Frank Marcos has corroborated that using different satellites and different technique, and John Emmert has corroborated that and carried it much further forward using his method, which is basically to study the orbital elements of every piece of junk and functioning satellites, everything in low Earth orbit. And he attempts to deconvolve the solar signal through use of indices such as the F10.7 and estimate what that change in thermospheric density is. And they all agree that at solar minimum it's in the order of 5% per decade. So this is pretty solid, and again corroborated by different groups using different data from different satellites. We've tried to carry the modeling forward using the 3D time GCM. That original result from '89 was using a 1D model, where we're now doing 3D simulations, and this is a simulation of essentially a solar cycle, 11 years of using actual carbon dioxide measurements as input to the model at the lower boundary. Those measurements coming from, of course, Mauna Loa. So the temperature goes down, and as the temperature goes down, the density goes down. This is for solar minimum. The change at solar minimum is larger than the change at solar maximum. And this is because at solar maximum, the change is mitigated to a certain extent by the presence of nitric oxide in the atmosphere. There's much more nitric oxide at solar maximum, and that changes the radiational balance in subtle ways. But regardless of solar cycle, you're always decreasing in density. It's just that the magnitude changes. Now, there's an interesting thing on this plot, which I'll try to explain as quickly as I can, which is that at solar maximum, the temperature change in the lower thermosphere is actually positive. And that is very paradoxical because it's right in this region where carbon dioxide is doing most of its cooling and shedding the heat from the thermosphere. The reason why it appears positive, and we really think that this is a real effect of the decrease in high altitude temperatures and an increase in lower thermospheric temperatures, even as in the middle atmosphere the temperatures continue to decrease. It's a very simple phenomenon. All that's happening is that as the atmosphere cools, it contracts. And when you have a strong positive temperature gradient, as you do in the lower thermosphere, The contracting atmosphere sags the temperature curve below where it started. And this is for a doubled case, so you can see the difference. The base case in red, you double CO2. Yes, the thermosphere cools, the whole thermosphere subsides, and in this narrow altitude range, the temperature actually increases because the pressure surfaces are going down. If you look at this in a pressure reality, as modelers tend to do, you don't see that effect. But in altitude space, in the real world, you really are getting a temperature increase here at the low altitude. If you couldn't see that on the plot, I just blew it up. So you can see that what's happening is that the one curve is sagging below the others. That's the only thing going on. So try to compare these to the models to the measurements, try to get on the right page. The blue is Emmert's estimate of the solar cycle dependence of the rate of cooling in degrees per decade. The green here is Marcos. The purple is Keating. And this is the global mean model result. This is our new 3D model result. I call your attention to this low activity estimate here. We are now in good agreement with Keating and Emmert that at low solar activity, on the order of 5% per decade. And here's that 5% per decade again. I'm now going to show you something on this plot that I didn't show before, which is that even though there's this 5% per decade trend, I stopped the previous plot at 2007 when we thought we were at solar minimum, showing you the trend in density, and neglected to point out that in 2008 and 2009, something else happened. The atmosphere dropped to 30% below the expected density. 30%. And that's even taking into account this 5% per decade trend. And that result has been published by John Emmert. We've actually made that calculation with a limited set of satellites ourselves using data that Bruce Bowman supplied to Liang Chen. Now, that's very hard to understand because if you look at some of your standard indices, it's a much greater drop than you'd expect. So there's a lot of debate about what might be causing this, even a NASA program to try to get to the bottom of it, and of course, comedy ensues. Sorry. Here are several of those solar indices and measurements. The F10.7 radio flux, the sunspot number, magnesium-2 core-to-wing ratio, Lyman alpha composite, and an actual measurement of solar EUV from the solar EUV monitor on the SOHO satellite. This is the one actual EUV measurement we have going back a whole solar cycle. And you can't see over a solar cycle on this scale what the differences are, so I did this to try to compare them in a consistent way, which is to say, well, let's take the annual average from 2008 minus the annual average in 1996. That gives you a delta. And normalize it by the expected range, which I estimate by the max to min range, the annual average in 2001 to 1996. So this gets away from this whole question of when you say, well, it was a 3% change in F10.7. Well, what does that mean? Because F10.7 starts at some arbitrary number like 66. So when you look at these various indicators on these scales, you see that indeed F10.7 was down, but not very much. Sunspot number on an annual average basis was down a lot, but that's mostly because there was these long periods of time where there just were no sunspots. And the sunspot number can't drop below 0. Just as we think the F10.7 can't really drop below about 66. The Lyman alpha composite and the magnesium-2 core-to-wing ratio composite, these obtained from Tom Woods and Rodney Viereck respectively, are in very good agreement. There's definitely uncertainties on these, but they have the virtue of being in the middle of the expected range, and they have the virtue that when you use these indicators in actual models, you get about the right answer. The SOHO measurement is controversial because they see a much larger decline than anybody else sees. And that may be due to drifting of the sensor calibration. It's one of these things where different analysts have looked at it in different ways and come up with different answers. So I don't want to say too much about that other than that this particular measurement is controversial. But it does see a very significant decline from one solar minimum to the next. So we're using actually the magnesium-2 quarter-wing ratio, but we could equally well use Lyman alpha as an indicator of EUV fluxes in the model. We put in the solar EUV change, the geomagnetic activity change, and the carbon dioxide increase. And we get, of course, a much cooler atmosphere and a much lower density atmosphere from 1996 to 2008. So when I showed this plot before, and we were talking about the dots and the solar rotation and the solar cycle, what I neglected to point out was that this solar minimum is, in fact, in our model runs and in the satellite data, 30% lower about than in the previous solar minimum. So a lot goes into that calculation. There's ongoing debate about the specifics of those causes. I think that it's becoming pretty clear that this is not some strange nonlinear effect of global thermospheric cooling because the atmosphere is largely recovered in the years since solar. And we're still, it's a weak cycle, but the model and the measurement are back in equilibrium, or still in equilibrium. We don't think that this is because something happened in the lower atmosphere that lasted exactly 2 years during solar minimum. The question of exactly how the sun went about changing the atmosphere, if indeed it were the sun, is still under debate. I show this just to show that we get the altitude profiles about right. This is from those model simulations using the solar change in carbon dioxide and then adding in the geomagnetic activity decrease, which is significant. And so when you include all of these changes, we get pretty good agreement with Emmert's data. Still, he found it slightly larger decreases than the model is predicting, but they're very close. And the slope, the atmospheric slope of the change is about right. And that tells me that there's no great mystery here. It tells me that it's at least possible that the model physics and chemistry are roughly correct. So if the thermosphere went down, and if the cause was solar irradiance and geomagnetic activity in some combination, then the ionosphere must decline too. So says the model. Our model says that from these same runs, with those same assumptions, it caused a 30% decrease in density. I should mention that the reason that a 7% change in the sun can cause a 30% change in density is because it's cumulative. It accumulates as you go higher and higher in altitude. At 200 kilometers, it's not that big a change. You get up to 400, because that whole scale height changed. You get a very big effect in the upper atmosphere. And that's why those thermospheric densities are so sensitive to this. It's a great way to detect it. So all that says that on average, we expect that the peak of the ionosphere should go down by about 14%. So is that really true? Well, the first way that this effect at solar minimum was noticed was actually from ionospheric data. Rod Heelis had a very noted paper and a talk at AGU that called everybody's attention to when the SINDI instrument on the CNOF satellite was launched. They got much lower ionosphere than they expected. People were saying, expected to be the ionosphere, but they're in the plasmasphere. If you don't know where the plasmasphere is, then ignore that comment. Since that time, there's been more than a dozen additional papers analyzing satellite data, ionoson data, radar data, total electron content, and all of them have found some degree of decrease with one exception. We're not voting here, but many observations have confirmed that the ionosphere is indeed lower in density and altitude than in the previous solar minimum, as we expect it should be if the density of the neutral thermosphere is lower. So we wanted to do some of our own analysis of this. This is work done by Alan Burns, analyzing data from a selection of ionosons. The measurement with a 365-day running mean and the model. and a line to connect the two solar minima. And this is just one ionoson that we analyzed, but we find that the ionosons and the model prediction for that location are pretty much on the same page, and the decreases are on the order of 10 to 15%. Here's a summary. Some of the ionosons we looked at measured changes running 10 to 15%, similar to what the model predict for that location. Here's, for comparison, an ionoson analysis done by the group at the Chinese Academy of Sciences. They've published several papers on this. They used mostly Asian sector ionosons, and they're actually getting larger decreases than we are for whatever reason. These are all derived from noontime measurements, which is the time when you would expect that if the sun is down, that the ionosphere would be down. At night, you get a much more confused picture. In fact, at night, it's possible that the ionosphere is actually a little larger. But for these noontime measurements, I think it's pretty good evidence. When we look at that global mean and derive from that long-term run a global mean peak density of the ionosphere, that's in red. That's with our previous convention. This IG12 index is derived from multiple ionoson measurements and is used by the ionoson community as an indicator of solar activity. It's just an index, imperfect like all indices, but as it happens, with this scaling, our estimate of the variability is on the same page, and indeed, both the IG12 index and the model simulations say that the ionosphere during the day was about 15% lower during the 2008-2009 than it was back in 1996. So both the thermosphere and the ionosphere were cooler, less dense, lower than during this recent solar minimum, the minimum between cycles 23 and 24, than during a typical solar minimum, and I use quotation marks around the word typical for a reason. We think the primary cause of this was the lower solar EUV irradiance, magnesium 2 quarter-wing ratio, Lyman alpha are very consistent with this. Lower geomagnetic activity during that solar minimum is important. It's a smaller contribution, we think, but it makes a significant difference and to the thermosphere and ionosphere processes. The secular change due to the increasing carbon dioxide levels are also important, but in this case, small, only about a 5% change from the previous solar minimum. And in the future, being able to go from one minimum to the next in order to quantify anthropogenic change is something that we will only be able to do if we have really, really good measurements of solar output during those solar minima, because the concept of a typical solar minimum is no longer tenable. So here are some papers on this subject, and here are my thank yous, and thank you all for paying attention.
Questions for Stan?
So you've been looking at the last two solar minima where F10 as a proxy seems to have fallen down in terms of a proxy for the EUV, but yet we go back from that point into history and there isn't much else to compare with. Is this recent minimum unique, or is there a possibility that the previous 40 years of EUV is also not going to track F10 very well, and we have no other alternatives, sunspot number being on?
It's unknowable, except when you look at, say, here's the Chen et al. They went back several. You got ionoson measurements going back some ways. You can look at the data from Chilton from back to the 30s. What I think is going on with F10.7 is, and we've talked about this before, it's unsurprising that sunspot number might fail at solar minimum. Because once it gets to 0, it's just 0. And if things are continuing to vary, it's not going to reflect that. And we've seen that before with the last Lyman alpha measurements. And F107 seems to do a similar thing. It gets to 66, and the continuum emission takes over, and it's no longer indicative of solar activity in and of itself. And we've seen that, again, with those Lyman alpha comparisons from SME and source. So once you get to a sufficiently low level, that measurement loses its traction. It has the opposite problem, as you know, at high solar activity. F107 will go jumping around in a way much larger than the EUV itself will. So it has these issues at the high and low ends of the spectrum, but it's still the most stable, reliable, available, dependable thing we've got. And that's why certain of my colleagues don't want to let go. And I don't want to let go either. And and every time the Canadians threaten to turn that thing off, I'll be the first to write a letter saying we need that measurement. And it's back in business. It's been doing fine the rest as we come out of the solar cycle. But just as at solar max you have to take that measurement with a grain of salt, at solar min you have to as well. But it looks to me like the last time activity got so low that F107 would fail was probably back around 1910 when they weren't making that measurement. The same thing applies to sunspot number. And the same thing applies to the Maunder minimum when sunspot number stopped. And therefore, what can we say about solar activity? Come back on Friday and we'll figure it out.
Question for Stan? I have a quick question on your explanation of the change of the density when you have CO2 increase under solar min and solar max conditions. You said there's a kind of puzzle. Yeah, this figure there. Okay, yeah, this figure is fine too. So you said the under max conditions that increase is because the profile is coming down a little bit. But that same thing can happen under solar minimum, right?
Yes, and in fact it does. This is a tiny island of increase there.
All right. Okay.
The reason that this effect is so much larger at solar maximum is because the profile is so much steeper.
Right. Okay.
Because do I have the? Yeah, you see, you're going. Well, if I have to go all the way back to the beginning. Yeah, you see this at solar maximum, you got a really steep temperature gradient here. So when the atmosphere settles, subsides, decreases in altitude a little, it doesn't make sense. How can the atmosphere decrease in altitude? If you're used to thinking on pressure surfaces, and who isn't? In our hydrostatic world, if you think on pressure surfaces, just imagine all those pressure surfaces sort of settling down as things cool off. And at solar maximum, this profile is so steep that you actually get heating. And basically the cooling from below, the whole atmosphere is cooling. And so the cooling down here is dragging the atmosphere down. And you get this apparent, this artifact, this apparent increase. I was discussing this, in preparing this talk, I was discussing this with Liang. And I have to come up with some kind of slide to explain this artifact, this anomaly, this apparent increase. And she said, no, it's real. And she's right, it's real. It really happens. The world exists in altitude space. Our pressure view of the world is flawed. But in a hydrostatic atmosphere, funny things happen.
By the way, this figure is from a global mean model, or is it?
This is EMSIS.
Oh, EMSIS. Okay.
All of the tutorial material here. This is, I should credit EMSIS and IRI. Empirical models thought to be climatologically good, but deficient in the detail.
More questions? No? Oh, let's thank Stan again.